So I think I didn't finish the introduction thing last week. So anyway, I wanted to finish that up and go to so there's a few like introduction things to do, and then single component systems, which is Clausius-Clapeyron equation, and then phase diagrams. So so that might take more than a week to do. But anyway, there's a couple things to finish here. So let's see. So anyway, I think I got up to well, I talked about the heat capacity. The difference in the heat capacity is this equation. So I want to derive that. And then I think I went through this. So we'll have a section on surfaces. So it'll be like solutions, phase diagram, single component, then solutions, phase diagram, phase stability, which is like kinetics kind of, and then surfaces. So this business of surfaces takes into play like nanoparticles. So one of the first things was to look at like the melting point of nanoparticles, which was, I think this is also from like Gibbs was in the 1800s. This is also from the 1800s, but basically if you have crystals that are smaller than a micron, then the melting temperature shifts, and it can shift pretty significantly. So to find out how that works, so you write the expression for the free energy, which you can get from the square. So G is VP and S minus ST. There's going to be H minus ST. G is H minus ST, right? So basically, if you have a transition, it's delta H. So delta G between two phases. So melting point between a liquid and a solid. Delta H, the enthalpy change. So that's a heat of fusion. And then delta S, right? So delta S is the thing you don't know. Delta H you can measure with a DSC. So we can measure the heat that it takes to melt something. But delta S you can't measure. So if you say you're at equilibrium, so the liquid and solid are in equilibrium, then the free energies of the two phases are the same, and delta G is 0. That means you can get rid of delta S. So you can say T infinity is delta H over delta S, or delta S is the enthalpy divided by the equilibrium melting point for an infinite crystal. In other words, a crystal larger than a centimeter, say, or a micron, something macroscopic. So anyway, so then you take this free energy expression and you add in a term for the surface area. So you have this surface area for the particle. It's going to be say if the particle is spherical, it's like r squared, right? And the volume's like r cubed. And so you just kind of simplify it a little bit, but so it'll be a geometric factor depending on what the shape of the crystal is. Okay, so these are volumetric terms. So you remove the volume, so you take the volumetric free energy times volume, the volumetric enthalpy, volumetric entropy times volume, and then the surface energy times the area. And then you swap out r cubed for volume, r squared for area. Then you'll end up with an equation and then you can divide. So you just have, because since it's r squared, you can divide by, and it's 0, so you just divide by r squared. So it's just sigma, that would be r, and that's r. So you can solve for r. You can solve for r, it's going to be sigma over this thing, negative, right? So basically sigma over that thing, and if you substitute in for delta S, this thing, so delta H over T infinity, you end up with this expression, like sigma for delta H times 1 over TR divided by T infinity. Or you could solve this for TR and find out TR is this thing. Right, so basically, the melting point of a nanoparticle should go with 1 over R. And then when R goes to infinity, this term goes to 0 and you get the infinite melting point. And for any finite R, you're deducting from that to get a lower melting point. Right, so whenever you're doing this kind of thing, you have to use Kelvin, right? You can't use a relative temperature. It has to be an absolute temperature. That's kind of one rule of thumb. So basically the best rule is just use Kelvin for everything you do and not use centigrade or Celsius or Fahrenheit. Because otherwise, if you do this in centigrade, you could have a negative temperature here and it would mess the whole thing up. So it wouldn't work. Anyway, so the theme here is that you start with the basic thermal equation and you add in terms that are going to deal with the problem at hand, which would be like the size. So that would have to do with the area of things. Or if you're going to add in, you could add in terms like this is a term we just added in, sigma AS. You could, if it's a force, you're stretching it. You could add in that term. You could add in the field effect. You could add in magnetic field, like electric field, magnetic field. Right. So probably anything else you can think of that would affect the energy. But these are the main things that people have used, if you're talking about polarization. And so anyway, so that's like the first example of a kind of a modified free energy to target some problem that you have to get an answer, right? Out of like, how is the melting point going to shift with size? There's an example of that in the notes. There's a paper where they do that, but they fail to do this one over R plot, right? It's in somewhere in here. Size dependent melting. So they don't do the one over R plot, unfortunately. Because of that, they don't. So they have the melting temperature versus diameter. So it should be 1 over diameter. See, there's a curvature to this. It should be linear if you did it 1 over. So yeah, that's one thing. It's kind of one thing that needs to be. Any questions on that or that stuff? So then, so it's kind of a story like this. Carnot, right, was a French an engineer, I guess, and he came up with Carnot's law for heat engines, right? And he wrote only one paper, and then so he died pretty young. He died at like 30. And then when he died, like his brother burned all his papers, right? But later on, this guy Clausius, not Clausius, let's see, Clapron, I guess. There's a French guy, Clapron, who found Carnot's stuff and then figured out it was important. And later on, Clausius, a German guy. So Carnot wasn't well known in his lifetime. And then he was like the seminal person who kind of invented absolute temperature scale, the idea of efficiency for engines, basically the idea of entropy, right? But he died like pretty young, and basically all his other papers were burned, So anyway, Clapron was a French guy who found his stuff and kind of brought it to light. Then Clausius is a guy who figured out that what he was talking about was entropy. It's like it kind of went through trading off hands from Carnot to Clapron to Clausius. And then Clausius kind of got famous off this entropy thing. And also Kelvin took Carnot's stuff and figured out the absolute temperature scale. So it was a British guy, Kelvin, right? So it was on the 1800s, but basically it was kind of a strange handing off of things. It led to this idea of second law that says that entropy has to increase in systems. So if it's a reversible system, entropy is 0, and following this definition of entropy, that means TDS equals Q. So if you have work as Q, if you have internal energies, heat and work, then the heat part becomes dST for a reversible system. That means when delta S equals 0, so you have no entropy loss in the system. Anyway, so that's kind of like the second law idea, is this idea of entropy, and it has to be bigger than 0 or equal to 0 or larger, right? So anyway, so that becomes like common thing to swap out ds swap out dq for tds. Like that's why q doesn't show up in the square thing, because you just have like TDS, like S and T swap out for Q, and P and V swap out for work. So that's kind of how this square thing works, right? So the Q and the W become PV and ST. So the second law gives you ST. The PV means you have no work other than kind of pressure volume work going on, right? So, which is a normal way to write things, right? So anyway, so that becomes, so anyway, if you have this so if Q at equilibrium, Q has to equal TDS, and that means that you have to have like basically Q minus TDS has to be less than 0, right? And then this thing becomes a definition of the energy that's available for the system to do things with, dq minus TDS, right? So basically that's like this thing would be 0 if there's no, that would be at equilibrium, right? And then that thing becomes some value for a change in the free energy of the system, like the energy that could cause work, right? So this idea of like, the idea came from Carnot, and then it kind of got handed off to different people, and Clausius kind of came up with this idea, and that becomes this idea for free energy, which really was something that Gibbs, who was a US guy, also in the 1800s, kind of came up with this idea of free energy, right? So Gibbs free energy, and then Helmholtz free energy, right? So Gibbs would be like the normal kind at atmospheric pressure, and Helmholtz is with constant pressure and with constant volume and variable pressure, right? So anyway, so that's kind of the scheme of this. It's like constant volume dq is u, so it's u minus ts, which would give you h, which give you a, the Helmholtz free energy, and then q is a constant pressure, q is h, so it's dh minus tds is this Gibbs free energy, h minus ts, which are all in the square thing. G is st minus st plus vp, and then, or G is h minus st, and a is u minus st. Those things, and also the derivative terms. So anyway, so then so that's like the second law, and then the third law is this thing that Boltzmann had. Like you can statistically figure out what the entropy is. You can define the entropy in terms of the number of states in the system, and then that can be used to do a variety of things, right? So basically, like in quantum mechanics, that becomes important, and also just in looking at modeling systems where you can count the number of states, that you can calculate the entropy, right? So it's possible, then the entropy kind of becomes a real thing. Like before, except in this Boltzmann context, the entropy is something that you're always trying to get rid of. Like in other words, you're using this expression to remove entropy because you can't really measure it. But in a computer simulation, you can measure the entropy. You got to measure it using this Boltzmann equation. Like the third law is like how to calculate entropy. Right, so entropy is, even with Clausius, is seen as like kind of a mysterious thing, right? And then all of a sudden it becomes something that's real. Like in other words, you can't count this in a real system because there's far too many states to count. But in a simulation, you can have the computer count the number of states, and you can calculate this thing. So so that's the idea of this thing. So if you, one thing it says is like if you have one state, then the entropy has to be 0 because log of 1 is 0. Log of 1 is 0 too, right? So, right. So in other words, something to the 0 power is 1, right? So basically, if you have one state, the only way to get one state is if you can get to absolute 0. Right. And if you're at absolute 0, there's no thermal motion, so it can't be an ergodic system, so you can't reach absolute 0. But this whole thing tells you that you can't actually get to S equals 0 because of this issue. You have to have thermal motion to be ergodic, and if you aren't ergodic, you can't use these expressions. right? So anyway, so all right, so that's kind of like first energy balance, second this idea of entropy and like kind of efficiency. Third is this business of Boltzmann, right? Right. So anyway, so there's a couple math things that have to be gone through, right? So one is like these Maxwell equations. We have all these differential relationships between terms. So you can basically to get rid of entropy. This is kind of the main theme of this. But so if you have some expression like ds dv, t, you can't get entropy, but you can get p, t, and v. So you can swap out that for this. And in the square, these are going to be the horseshoe rules. You have negative ds dv at constant t is the same as negative p dt at constant v. So ds dv at constant t is p dt at constant v. So you go like draw a horseshoe and take this by that at that, and this by that at that. Those two are equal, and you take the first one that has a negative sign to give the sign. Like dv dt at constant p, btp, it's going to be the same as spt, right? And there's a change in sign because the s has a negative. So it's minus. Right, so it's four corners. You have four Maxwell equations that relate those. So where those come from is this kind of math trick called Legendre transform, right? So it sounds complicated and kind of is and kind of isn't. So you have this expression. So the internal energy is the heat and the work, right? So PDV and then TDS. This is for reversible. That's for only expansion contraction work. So this is the normal thing that you get from the square, like du is PDV TDS. Right, so that's that thing. So you can get, using that, you can get 8 DH is BDP TDS, etc. Right? You can get each of the middle ones defined in terms of a differential equation. There's 4 differential equations in that thing. Right, so anyway, so if you have that differential equation, then you can say du ds is going to be t, and then du dv is going to be p. It's going to be minus p, right? Because du ds constant v is t, du dv constant s is p. So let's just take that expression and say, what if I hold the other thing constant? Then I get these differential, kind of partial differentials for the thing. Then you say, then you can write an expression and say that this thing is in terms of s and v. So I can say du is ds and dv, which I already had, and then swap out these differential terms for it, like du ds constant v, du dv constant s. So it looks like a little game, but basically you're doing that because then you can say, then you can take the second derivative of the thing. So this is a repeat of that thing. And then you can end up with, if you do du ds dv and hold it at constant v, then the v term drops out, right? And if you do du ds du dv ds, then the s term drops out because the s is held constant. So in one case you hold the v constant, the second case you hold the s constant. You end up with du dv ds, du dv at constant s ds, and this is dv of the other one. Held at v and s have to be equal to each other. So it's just writing the same, taking the same derivative with respect to v or with s, and you'll end up with these two terms. Then once you have that, then you end up saying that du ds at v has to equal, let's see. Then oh no, because du dv at constant s is p, negative p, and du ds at v is constant, is t. That means you can swap t and v. These two things are equal to each other. So if you swap in p and t here, you end up with dp ds v, which is the Maxwell. So the whole Legendre transform is to just mess around with get the differential equation, write it in terms of differential terms, and taking the second derivative. Then if you held the other one constant, then you end up with these two expressions, and plugging in what those partial differentials are, and you'll end up with the Maxwell from it. So it's kind of a game. I mean, you don't necessarily need to know how to do that. Basically, that's where these things come from. And I'll show you in getting the heat capacity difference, like why you might want to do that, because you need that. You need these rules to get out of trouble when you're doing calculations of the differential, like trying to figure out what CV and CP difference is. Then you have to have this kind of expression. Okay, so anyway, that's the Legendre. It's in books. You can Google it too if you want. But basically, that's what it is. Basically, it's not as anyway. If you look at it, it kind of makes sense, but it's just a bunch of steps, you know, so you get lost in it. Anyway, so is that business. Then yeah, so then if you that was the DU one, which gave you this, and there's also you can do it with the DH expression, the DA, so the Helmholtz and the Gibbs free energies. You get these four Maxwell relations. So when you're trying to solve differential, and again, like these things are the horseshoe things, you do like negative ds dv at constant t is the same as pt at constant v, dsvt dptv, right? So that you just do a horseshoe on the square and you can get all those, one for each horseshoe. Right? So, and then also the inverse of these work too. So if you have dv dt at constant s and ds dp at constant v, I mean, those are equal too. I mean, they have a negative, right? But so basically, if you run into the inverse one, it's the same as you just have to invert both of them. So, which is that comes up to be like so there's a series of these differential equation rules, like invert dx dy at constant z is the same as 1 over dy dx at constant z. So that of the 4 Maxwells is actually 8 if you do this inverse thing. Right. And then there's a bunch of these kind of differential rules, like dx dy at constant x, since x is held constant, the change in x is 0, so that thing's 0. Right. And then if you hold y constant in the bottom, that becomes infinity. So 1 over 0 is infinity. So if you apply this rule, the second part of this rule, you don't need to say because 1 over 0 is infinity. And then dx dx, the change in the thing with respect to itself is always 1. And these kind of more complicated rules that don't necessarily make that much sense, but basically they work. So the chain rule, so I mean dx dy at f is dx dz. So you're introducing another term in the chain rule. Then the expansion rule is also kind of introducing another term. Then the triple product rule is just weird. Like you have 3 terms and the whole thing equals -1, right? So it's kind of like in desperation, these are levels of desperation. These things are pretty simple. This is a little bit more complicated. Then finally you reach for this triple product rule when you're desperate. That'll relate 2 differentials to a third. So if you want to get rid of a term like S, usually, then you can use these kind of things to mess around with it. Anyway, so that's that business. Then, all right, so I wanted to go through this, how to get this expression for the difference between the constant pressure heat capacity and constant volume heat capacity, right? So from these differential equations. So there's a couple things that come out of this, like first that each of the heat capacities is going to be related to the entropy, which isn't necessarily obvious. Like it's kind of obvious it's going to be like Cp is dH dt. I mean, it's like the heat that you put into the system with respect to the temperature is kind of is what the heat capacity is. Like the heat capacity is how much heat you have to put in to change the temperature. That's just the definition, right? So in the case of constant volume is du dt. Basically, the pressure one makes sense, right? So these expressions are like order. So you have the heat capacity at constant pressure is the entropy with temperature at constant pressure times temperature. So when that comes out of, so we have like oops, let me move this guy. So dH is VDP TDS. dH is VDP TDS, right? And then if it's a constant pressure, this term drops out. That means dH is TDS and CP is dH dt. So you put the dH in there, which is TDS, end up with TDS dt at constant P. right? That term drops because it's a constant pressure, right? So that gives you this weird thing that the heat capacity is a change in the entropy with temperature times temperature, right? And the same thing goes if you do du is pdv TdS from the square, right? Then if you say constant volume, the second term drops out, and then it's going to be then you're just going to have CV as du dt, which is just going to be TdS. So T times ds dt at constant V. It's the same thing. The heat capacity is a change in entropy with temperature times the temperature. So that's the second definition of the heat capacity. And so the first is dq dt, right? And then the second is going to be, if you say constant volume du dt, you say constant pressure dh dt, and the third is going to be T times ds dt. So heat capacity has kind of like 3 ways to talk about it. 2 of the ways have 2 ways. So that gives you like 5 ways, I guess, to talk about the heat capacity, to define it, right? So anyway, you need this ds dt to figure out this expression. Okay, so but this thing in itself is really useful. Like later on, that'll be like a main thing that we can use. Right. So anyway, so since you're dealing with S, then you write a differential expression for S, and you're dealing with like T and V. So basically, or you could pick any that you want, but basically T and V will give you this answer. So you say ds could be broken down into temperature and volume. So any 2 parameters you could have used. But it's going to, so then the lead to that is going to be ds dt at constant V, ds dV at constant T, right? So you have ds dt at constant V, that's CV. So that's good, you can pop it in, CV by T. So the first term already solves a problem. Like you're trying to relate CP and CV. So you have CV here. Then you have this weird guy, dP dt at constant V. So what do you do with that? Like you're stuck at that point because that isn't a heat capacity. Like there's no heat in that, it's pressure, right? So there's no H or U in it, right? So anyway, so to get rid of this, so you need to get rid of this thing. So this is how you do these differential things. You end up, I can do that, and then finally you get like, what do I do now? So you have no idea. So then you go like, well, you go back to that chain rule thing, right? So you can introduce a new term. So you get dx dy, you can do dx dz dz dy at constant f, right? So you introduce the new term. Let's see, where am I now? The PDV we needed 2 chain rules. Introduce the chain rule would be like dPdV. V is a new one, and then dV dt, the constant p. So that comes by substituting in that chain rule thing. And dV dt, constant p, is the thermal expansion coefficient. It has a volume change with temperature at constant pressure. That's alpha by V. And dV dP, okay, change in volume of pressure is the thermal compressibility. So it's constant T divided by volume. So kappa T by V, and alpha is the thermal expansion by V. The V's cancel and you have alpha by kappa. So this thing is just alpha by kappa because you are able to do this like math trick here. You took this thing and you changed it into 2 things that are knowns. Right? Remember in the paper he's talking about the what is it? The response function, thermodynamic response functions, which are heat capacity, thermal expansion, and compressibility. So those are numbers you can look up in a table, right? Like you can measure those numbers, you can look up in a table. So basically, or on the web at the NIST web book, which I'll show you later on. Like you can get all these numbers on the web. Anyway, so that simplifies that term. So you can just pop that in here. Then you're going to have like that this expression is alpha by kappa dV, and this is dt. And then what you want to get to, you have CV, so you want to get CP, which is ds dt. So that's ds. This swapped out for alpha by kappa, and then ds dt at constant p. So you want to take that guy. So dt is going to give you 1. So you have CV by t. So that's one of the rules, like dx is going to be 1. Change in temperature with temperature is 1. The change is the same, right? So, and then you have this volume term, which can d volume d temperature at constant pressure, which is, that's the same thing you had before. That's the thermal expansion coefficient divided by volume. So you're going to have alpha squared times volume divided by kappa. You have CV dt here, and this thing is CP dt because I said ds dt. So you got the relationship between CP and CV. If you rearrange that thing, you get that thing. So that alpha squared by kappa is there. The volume comes from here, and these are both divided by temperature. So you multiply by temperature and get that thing. Right. So all right. So you can look at this and say volume's always positive, temperature is always positive. These are absolute, right? It's absolute temperature. Thermal expansion is usually positive, except a couple weird cases. And then kappa's compressibility is positive. That means that CP is always larger than CV, which you couldn't have said without this expression and going through this weird math. You could never have said like, which is bigger, like a constant pressure or constant volume. So it has to always be larger because all these things are positive, right? And you can calculate it out, and you can basically, that allows you to count. So it allows you to say things about thermodynamic parameters that you couldn't have said, right? In other words, by using this differential stuff, you can start saying general rules about the world, right? Based on just the math of it, that it has to be a certain way. Any questions or anything on that? Or so then you can, so if you take like, so does the free energy decrease with temperature? This is a question. So you can write dg, it's minus sdt vdp. And if you say dg dt, a constant p would be like negative entropy. Right, so you have, and you know that like say the entropy is like the randomness of the system, and as the temperature increases, the randomness increases. Right, so that means that this is a negative, so that means dg dt has, in other words, dg dt, if this is a positive number, this thing has to decrease. So the free energy has to decrease with temperature just because of this expression. Right, so anyway, so this is another case where like, so you can take, this is many of these cases where you can say the general behavior of things based on these differentials tells you how the trends of the thermodynamic parameters are going to go. So you have like the liquid free energy drops, the gas free energy drops, then where they cross, that's the equilibrium point where the liquid and gas are, in other words, where you're vaporizing the liquid. Right, and then you have the dropping of the solid, dropping of the liquid, they cross at the melting point for energy. And you could say like, why is the solid and the liquid have different slopes of free energy with temperature? It's because the entropy is different between the two. In other words, the entropy of the solid is lower than the entropy of the liquid. That's why it's got a lower slope than the liquid. The entropy of the gas is higher. There's a randomness of the gas higher than the liquid. That's why it's got a steeper slope, because the slope of GT is this S. So you can actually say like everything about this phase behavior plot, which defines the boiling point and the melting point just based on this one differential equation. You can just say everything about it. You know, so it's like really powerful. But you can start saying like why the world is the way it is, with some kind of understanding of what the mechanism of it is. Right. So anyway, and then why does G increase with pressure? It's the same thing. dG is SDT, VDP, right? And if you say at constant temperature, then it's going to be the volume. So the volume, so you can say like volume's positive number, that means that this thing, so volume is always positive, that means G always has to increase with pressure at constant temperature. Right. So this is specific volume, like 1 over the density. So the specific volume of So the slope would be higher so the slope would be, for denser material, the slope would be lower, right? So diamond's denser than graphite, so it's got a lower slope than graphite. Then at the intercept point where the free energy difference between diamond and graphite is zero, that's the transition point where you transfer. So if you want to make diamond, it's going to have a lower free energy, then you have to pressurize to like above like 1.6 gigapascal. So 1,600 megapascal for 16,000 atmospheres. It's a lot. And you need a diamond press to make diamond out of graphite. Right. So basically you can say a lot about things by kind of just messing around with he's got a few other things in here. So, yeah.
In terms of the diamond, the natural and artificial, which one is more expensive?
It depends on the market value, I think, they just found the largest, fifth largest diamond ever found in Botswana, like last week, I think. That guy's rich, I guess, that found it, or the company. The diamond, the natural diamond is kind of a weird market, because it's really controlled by that De Beers company in South Africa. So they actually have tons of diamond. They leave it in the ground. Like Botswana's got big diamond mines. They get kind of rich off it. So the diamond thing is a weird issue. I think that the price of the natural diamond is manipulated totally by one company. And if they actually released all the natural diamonds, it would be pretty cheap. But they're holding on to it. So it's a manipulated market. I think that the natural is much higher than the synthetic. But you can't make a diamond like the one they just found was like this big. So you can't do that synthetically because you need a press like the size of a building, and that's not exactly worth it because the use of it is going to be for like making polishing stuff. Because the hardest material, so just to grind, to make little teeny particles to grind, that's the industry, I think, for synthetic. There's research that makes something a little bit larger, but nobody, I don't think, makes these gigantic stones. So that one probably end up in a museum anyway, right? So it's a manipulated market. The price is artificial, but the synthetic ones are cheaper. But they're different too. They aren't. I mean, the natural colors of it and things. So you get that from weird additives that came from someplace, volcano or something, however they're made. High pressure stuff under the bottom of the earth, whatever. So they aren't necessarily just absolute carbon, right? So that I don't think you can duplicate that exactly in a lab. So anyway, that's my opinion on it. Let's see. So the Gibbs free energy. So I think I mentioned this already, but basically you want to talk about like ice and water. So you have like crushed ice in a glass and it's sitting on the table, right? Then eventually like it turns into just one solid chunk, right? I mean, so basically it's because the water atoms are jumping out of the ice into the water and the water atoms are jumping into the ice. So they're jumping back and forth all the time. And the problem is the surface area term. There wants to get rid of the surface area to minimize the energy of the system. So basically, the thing that's in equilibrium at that, if it's at 0 degrees C, is this chemical potential. So the jumping liquid into the ice, or jumping ice into the liquid, or liquid into the vapor, it's this kind of change in the free energy when you pull one atom out that matters, so 1 mole, right? And then that's the chemical potential. So you talk about, you could also write this like the molar Gibbs free energy, like put a bar over it, and it'll be like the Gibbs free energy per mole, right? So that molar Gibbs free energy is the same thing as this derivative term, which is the chemical potential. So equilibrium is defined by the chemical potential. So the chemical potential is going to be, say you have 2 phases present and 2 components or something, right? So basically it's going to be the chemical potential of something in some phase. It's going to have like 2 qualifiers to it. So you have to say the chemical potential of water in phase A equals the chemical potential of water in phase B. It's not going to be the chemical potential of the whatever salt in phase A equals the chemical potential of water in phase B. So it's like water, water, salt, salt, but in phase A and phase B, the phases swap, right? So here's pure water and pure water in the vapor phase. Those two chemical potentials, when it boils, have to be equal at the boiling point. Right? So, and then the amount of the phase changes by the amount of heat you put in to swap it from liquid to vapor. So they're in equilibrium all the way through, but the heat kind of moves the thing from one phase to the other. So let's see, at an equilibrium point. All right, so that's one thing. Oh, and then this is the last thing in this chapter, the Gibbs duum, which seems like it's a really kind of weird and kind of seems like a semantic thing, but basically it ends up being really useful if you can say that this thing, that the number. So if you can sum up all the phases in a system, and then say like the number of atoms in that phase tend to change in the chemical potential has to equal 0 for the system. Like in other words, component A, component B, the number of moles of those times their chemical potential has to sum to 0. Right. So and then with the other, so it's anyway, so this is used in a paper. It's kind of hot by this window. Get that COVID shot this weekend. I still probably have something lingering from it. Maybe, but what did I do? That's what I want. That's what I want. There. This is what I want. So this guy's looking at like corrosion. Let's see, this was a homework once, but I thought it was too hard and gave up on it. Let's see. Yeah, so he's calculating the chemical potential change in this electrochemical system from the VDP, basically. Right. So that's the Gibbs duum equation. And he uses that to predict I think it's like the plating of metals onto a surface or something. So anyway, so people use it when they come into kind of situation of desperation. They end up using this Gibbs duum equation. So he's saying that it's at isothermal, so he's using just VDP, and then the chemical potential change. And he's calculating the chemical potential of the two phases and figuring out what the equilibrium kind of pressure and density would work with this thing, right? So we'll see that we use this, like this you pull out of your hat, like sometimes it just shows up. So it's kind of a funny equation, but the derivation of it is that the Gibbs free energy, since these are derivative terms, dGdN, so if you multiply chemical potential by the number of moles, you get the Gibbs free energy. And if it's a binary system, A and B, then it's number of moles A times chemical potential A plus B gives you the total chemical potential. You take the derivative, you get 4 terms, like derivative first times second, second times first, right? And then you can also say that dG is this thing from so dG is the SDT minus the SDT plus VDP. And then you add in the chemical potential term if you have multi-component system. So you have to sum in the chemical potentials times the moles, right? So these two things have to be equal. And this guy has the same thing in it, right? He's got mu times NB, mu times NB. So those two terms are the same as this term, and he's got these 2 extra terms, right? So if you say a constant T and P, then you end up with well, from this thing, you end up with that, and that has to equal that. That means that this other, the du, n du, n du terms have to equal 0. Just because of the way this works. Like this has to be true, that has to be true. If you say constant T and P, then that has to define that this thing, this thing has to be 0, which means that. And then if you release the T and P constraint, then you just have that expression, which is this Gibbs-Duhem equation, which allows you to relate changes in the chemical potential to like the pressure change in the system, which it's meaningless until you apply it. So basically there's that paper where they're applying it, and and we'll apply it later on. So right now it's just something to show you that it's there, and you probably heard of it before and maybe never used it. So basically we'll use it later on. So it's just thrown in here to kind of look at. Anyway, that's kind of the end of this intro part. Those are like the major, supposedly all that stuff you should have from undergrad. Like that's the idea. Like all those things you should have seen before, theoretically. Right? You may have not, but basically now that I said them, you're kind of responsible to say that you know them. However, you need to go about getting to that point. This square thing can really help a lot. I mean, it can give you like all the answers. You may not understand what they are, but basically you can get the answers and you can work out what they are. So the homework, I just graded 1 because I only had 1, and then I had other stuff I had to do, so I didn't grade the rest of them. So did everyone turn it in though? I think I didn't even check to see if everyone turned it in, but I think everyone turned it in. And you figured out how to do that, right? And everything. So that's good. So I'll grade them. I'm kind of busy today, so probably I'll grade them tomorrow sometime. Kind of busy tomorrow too. Basically, I'll grade them before the next class, and then maybe I'll go through it. The one that I saw was perfect, didn't have any problem. So hopefully it's all okay. Any questions on that homework though, or anything? All right, so anyway, I wanted to go to this next, so I'm gonna kill this guy. Find the other guy. So this chapter, that'll probably take 2 weeks to go through this chapter, even though I don't know how many slides are in here, 47 slides, but basically there's enough stuff in here to kind of go through, like maybe it'll take 2 weeks to go through it. Very spent part of today, like an hour of today, I guess, but so I want to get through. So this is about single component. So basically Clausius-Clapeyron equation, and then the phase diagrams, I think is mostly what's in here. So there's a couple single phase diagrams, right? So like TP plots and things. So anyway, so like ice melting and boiling things, supercritical point, stuff like that. So anyway, so the book, if you look at the books, again, like the book is on the web page at the top. I can figure out that again. So up at the top here, if you click that, that's kind of the book that I more or less use to write the notes in here. And then I've added stuff to it, but basically I'm following his theme here. So foundations, what I just did. So you can look like all the things I said, like the Gibbs-Duhem equation, that's all here. And then single component, that's what I'm doing now. So basically, you can read that stuff if you want, it's in there. I mean, but one thing that's weird about the book is that he uses like strange transitions, like this Mott transition. So let's see. Is click yes, enable hyper, but won't answer it. Didn't do it. This is something that like, oops, that's not what I wanted. transition. That's not what I need there. That's, maybe there is no wiki page for that. Oh. I don't remember what the Mott transition is. I guess it's metal to insulator transition, which I guess is a first order transition. So that's what I mean. He picks up these things you've never heard of, essentially, but you get rid of that. Back to here. All right. Understand that. So anyway, so he's got so there's a discontinuity in the derivative property, and then there's a step function in the state functions. Right. So the entropy goes through a step change. There's like a change in entropy at the transition. There's a change in enthalpy. So there's a heat of transition for this Mott transition. So he's taking this nickel sulfide and heating it up, and then he goes through this Mott transition where it goes from I guess at low temperature, it's a conductor, and then it becomes an insulator at high temperature. No, probably the other way around. Insulator at low temperature, conductor at high temperature. Right. So basically the electrons are like frozen up at a low temperature, then they can flow at the high temperature. Right. And it's a first order transition. It's got a heat of change. And the Gibbs free energy of the two phases, so the conductor and the insulator, are the same at the transition point. So this thing just shows us swaps. That means G is H minus TS. So the H up and the minus TS up. So this S times T, that gap would equal this gap. That means the G is 0. Right. And the T dependence, because S goes through a jump, the T dependence changes of G. That means that anyway, the heat capacity is going to be like the slope of these two. And because the derivative of this in temperature, because it has an infinite slope here, becomes infinite. So dH dt, the constant P is infinite there, but there's a change in heat capacity between the conductor and the insulator. Right, so that's kind of a signature of a first order transition. Like he's mapped it out here. I think the reason he chose this, right, one is that he's trying to introduce every possible kind of transition in materials, especially in electronic materials. So you run into like a lot of, or magnetic materials. So you run into a lot of strange transitions. It's not just melting point, which is in glass transition, which are the things you'd normally run into, right? The ferroelectric, paraelectric, and ferroelectric, paraelectric transitions are like popular in this book, right? And then also there's magnetic transitions that he talks about. I mean, there's magnetic. Well, those are magnetic transitions, and then electrical transitions. I guess like this Mott transition. Anyway, there's transitions that you've never really heard of, right? But anyway, this is here, so it is a first order transition. Normally, when you're talking about that, it's a melting point, like in materials. Like you're looking at the heat of fusion. The reason, one reason not to do that is this heat. It isn't so clean cut as this. Like this is measured in a DSC. You go through this transition, and everything is like squared out. But in a real transition, these things are like rounded out, so they aren't necessarily so clear cut that there's a delta function here. And then the heat capacity is a broad hump here. It isn't like just a spike. So I think the reason he's going to a Mott transition is just shows you what it should look like in a model situation where you don't have like kinetics involved in it. So like you have different size crystals will melt at different temperatures. So things made up of grains that have different sizes, and this is broadened out. Each one of them has a different delta function. They add together into like a Gaussian curve, Gaussian peak, right? So anyway, so that's all. That's like a single component system going through a transition. I guess that's the bottom line. And again, the infinite crystal heat of fusion is going to be the ratio between delta H by delta S. And that's the thing that's used over and over again. Like T is delta H over delta S. It makes sense because delta S needs T with it to make energy, and delta H is energy alone. So basically the ratio of 2 gives you a temperature, that's a melting point of the, or the transition temperature for whatever the delta H is for. So let's see, this guy's gonna work for me. And then second order transition, this is, so what he uses here, again, it's kind of like, so normally you're talking about glass transition as a second order transition. He's using the crystal structure of alpha and beta quartz transition. So two crystal forms. So what happens in a second order transition is that there's no, at the transition point, there's no structural transition between the beginning and the ending of it. In other words, you take a liquid and you turn into glass. If you do a diffraction pattern in the liquid and diffraction pattern in the glass, they're identical. You can't tell the difference between them. But if you look at it in terms of like the change in volume changes, now the change in volume, the temperature, the slope of it changes at the glass transition. If you do a melt in a crystal, you do diffraction in the liquid, it's got an amorphous halo, and in the crystal, it's got a bunch of spikes in it. So there's a dramatic change in the structure. It goes from totally ordered to disordered, right? Whereas in a second order transition, they look the same above and below. The only thing that's changing is like the rate of change of the thing, right? So he's got, what does he have? Temperature variation in Gibbs free energy. So unit cell volume here. So at the transition, the unit cell volume is the same between the two. Like if it's a first order, there's a big change in the density. Like the liquid and crystal have a different density. Here, the line is continuous, right? In other words, it shows a corner, but basically at the point of transition, above and below, it's the same value. And then the heat capacity changes between the two because it's a derivative term, right? So in other words, the slope changes between the two. The way he shows this, some of these plots are weird. Like he has a peak in the heat capacity. So the area under that would be the heated transition normally. So he's saying that there isn't really a peak here. There's just a change in value. So I don't know. So the lower temperature phase, alpha phase, has a heat capacity that's not really linear. And then all of a sudden, there's a change in the value of the slope of the change in enthalpy. In other words, this is the enthalpy. It doesn't have a delta like a heat of transition. It's just got a change in slope. But that derivative of this with temperature is showing this weird curvature, and then that has a delta function with the slope changes at that transition, which you can't see in this plot. So I guess anyway, it's a little confusing, this transition he's using. If it's a glass transition, this is a lot cleaner to see, you know. And the free energy is just continuous through the transition, right? So the idea is, I think he's obfuscated the thing because he's using these weird transitions. Basically, first order should have a peak in the heat capacity, which is the heat of the phase transition, and a change in value above and below. And then entropy has a discrete change, enthalpy has a discrete change, and the free energy continuous through with the change in slope. And then the second order, the free energy is constant, it has a continuous behavior, enthalpy has a change in slope. Heat capacity should just change in value. You shouldn't have this peak in it. And the volume should be a continuous function with a change in slope. But here the slope actually goes negative. So it's got a negative thermal expansion coefficient in the beta phase, which is pretty weird. Right, that's normally something that you don't see. So he picked some kind of oddball transitions that demonstrate this from the book. All right, so this is what the homework's about anyway, the Clausius-Clapeyron. So, and this is basically for looking at the pressure dependence of transitions, pressure temperature dependence of transitions, like how, so typically this is used for the vapor pressure for boiling. Like you want to know what the vapor pressure is at a different temperature. And this equation gives you the vapor pressure at some other temperature. It's like if you want to know what's the concentration of some component as you heat it up in the air, you can get this from the Clausius-Clapeyron. So this thing, anyway, this is the equation dp dt. So you get it, start out with dg is s dt vdp, right? vdp minus s dt, right? And then if the chemical potential, so the dgdn's for the two phases, in other words, generally liquid and vapor, are equal, then you can say the liquid part and the vapor part have to be equal. This differential equation has to be equal. Then you're going to end up with a dp dt, so p and t. So you can get all the dt's on one side, dp's on the other side, then divide dp by dt. You'll end up with delta S by delta V. Defines the change in the vapor pressure with respect to the boiling point temperature, like how or the vapor pressure at a certain temperature. Right, so it's going to be this ratio. And then if you want to get rid of S, then you say again, like delta S is delta H over transition temperature. So you swap that out here, then you end up with dp dt is delta H over transition temperature times change in volume. So that's called the Clapeyron equation. Clapeyron's the guy that took the stuff from Carnot and kind of figured out entropy from it, more or less. And then Clausius is a German guy. So Clausius took Clapeyron's stuff. Clapeyron took Carnot's stuff, and then Clausius took Clapeyron's stuff. Right, so Clausius-Clapeyron doesn't mean that they work together. It means that he took Clapeyron's thing and kind of modified it a little bit. All right, the Clapeyron equation can be used for the dependence of a melting temperature on pressure, like you have a solid, right? And it means that the melting temperature, since this thing is a constant, because the change in volume between a solid and a liquid is small and kind of constant at different temperatures, then basically you can just use this equation to say that the pressure and temperature are proportional to each other because this is a constant. So if you look at, I think there's a plot in here, someplace. Here, heat of fusion and pressure. That's linear. In other words, delta H over T delta V for a liquid to solid transition means that there's a proportionality between the melting temperature and the pressure. If you want to get a higher melting temperature, you get a higher pressure. I mean, it depends on the sign. If it takes heat to boil it or if it consumes heat when you boil it, right? So some things take heat, some remove heat. So this can be plus or minus this delta H. So it's linear in any case, but it's either increasing or decreasing. So you could either increase or decrease the melting point by applying pressure. That's the idea. But again, it's in gigapascal. So that's 10,000 atmospheres per unit there. So it's like a lot of pressure. Anyway, so that's the Clausius, that's the Clapeyron equation, right? And then Clausius did that for liquid to vapor transitions, like chemical engineering transition. But materials don't really use liquid vapor much, right? Unless you're doing vapor deposition or something. So anyway, so if you're doing a vapor, then this thing no longer becomes like a constant. It becomes dependent on temperature. So that means you have to put in what this delta V is, and the liquid volume is almost nothing, and the vapor volume is huge. You just called the delta V the gas volume. And if you use the ideal gas law, you say the volume's RT over P, and you substitute delta V for this RT over P, and you end up with RT, and there's also a T, so it's D squared. And then the P term, dP by P is D ln P. So you get D ln P dt is this thing. That's the Clausius-Clapeyron equation. So that indicates you would plot ln of P versus 1 over T. Because T squared, say dt T squared ends up giving you T. If you integrate this thing, you get, oh, this thing's integrated someplace here. Here. So if you have let's see. T squared dt is 1 over d1 over t. d1 over t is t squared dt. So you end up with ln of p is ln of p goes with 1 over t, which ends up being this plot of pressure versus let's see. It ends up being a log of pressure versus 1 over temperature from this integrated form of a. So log of pressure versus 1 over t should give you a straight line, and the slope of the straight line is going to be this enthalpy of vaporization, pi by r. Right, that's the Clausius-Clapeyron for liquid vapor transition. So anyway, so that's like a good general rule to predict the vapor pressure of something as a function of the temperature that it's at. So that's used all over, and chemical engineers use that all the time. Right? So basically, that's like a chemical engineering thing to look at processing of liquids. Then, if you want to go further, oops, no, stop doing that. Go away. All right. So anyway, if you want to take that further, this P reference. So because you're doing an integral of this, you have the thing to something else. For the something else, you can use a critical, which is tabulated, the critical pressure, critical temperature. Then this whole expression becomes this like universal equation to predict the vapor pressure of anything at any temperature. So PR means the pressure divided by the critical pressure, and TR means the temperature divided by the critical temperature. And this omega is like a fudge factor kind of. So you can look up the critical temperatures in this acentric factor. This is a fudge factor. And then you can predict the vapor pressure of anything at any temperature. Like these are tabulated online. You can get the critical temperature, critical pressure, and this eccentric factor. Right, so it gives you kind of like a universal, that's like the chemical engineering equation to predict vapor pressure of things. Anyway, so there's that business. Oh, that's called the shortcut vapor pressure equation. So it's just like a way to get the vapor pressure. And this is just showing like where the so if you have pressure, so if you have the ideal gas law, PV over, so pressure goes as 1 over V over R over V, TR over V for the ideal gas. So pressure versus 1 over V is a swooping down curve. So that's at high temperature. That's at 500 degrees C for what? For water, right? So at 500 degrees C, water acts like an ideal gas. That's an ideal gas curve. As you cool it down, it starts to develop this kind of hump, which has to do with the association of the water atoms. So they have polarity, so they kind of attract each other in a certain way. So it leads to this hump in the P versus V curve. At some point, that attraction becomes enough that it separates, that the water will separate into a liquid with a vapor that's in equilibrium with it. So you have like pressure, volume, liquid, and vapor in equilibrium with each other. Right. So the exact point where you go from ideal gas to like 2 phases, that point is the critical point. So that'll be down here will be the critical density, or 1 over the critical density, and the critical pressure, and the temperature where that happens, critical temperature. So it's like a magic point where below that in pressure or temperature, or above that in density, you get 2 phases, and above that you have a single phase, which is a supercritical phase. Right. So basically, ideal gas and then the interactions show up. Then you get the critical point. Then you get to a critical point that some of the atoms will go into a liquid phase and some will go into a vapor phase, and they're in equilibrium across this tie line. So that phase and that phase are in equilibrium. So in other words, the Gibbs free energy of the guy here and the Gibbs free energy of the guy here are the same. Right? They have the same chemical potential across that. So you can make an equal plot of like chemical potential versus specific volume, and you could see that it had 2 points, 2 minima. It would have 2 dips in it, and those 2 dips would be the minima that correspond to the equilibrium phases that are in equilibrium with each other. So anyway, this is just here to show you like what a critical point is to do this reduction of that thing to TC. So the critical point for everything is tabulated. Basically, you can look it up. And then you can use it to get a universal equation to get the vapor pressure. Anyway, so you end up with this plot, which is like log of something versus 1 over t. And the slope of the line of that is going to be the enthalpy in the Clausius-Clapeyron equation, enthalpy of transition. Right. So there's a lot of there's 3 other places where you see plots of log of something versus 1 over t. So it's kind of important to figure out like what's going on here. So in the case of Clausius-Clapeyron, so this is like a convenient, it's like an equation that came out of convenience. Like, you had this equation that looks kind of complicated, but it turns out that like t squared dt is the same as d1 over t, and d ln p by p, dp by p ends up the same as d ln p. So you end up with ln p and 1 over t as the arguments. And because of that, it ends up giving you this plot of log p over 1 over t, and the slope ends up being the enthalpy. So it's kind of it's like an odd way to get to this. So get that plot, right? So the same plot you get if you do Arrhenius function, right? So you have some process. So in this case, you're talking about vaporization, right? A liquid goes to gas. So there's a barrier of the atom and the liquid that has to pop out into the gas. It's like kind of an energy barrier that it has to overcome, right? So anytime you have an energy barrier that something has to overcome, it follows this Arrhenius equation, which is also from the 1800s, around the same time as the Clausius-Clapeyron. Right? Arrhenius was the guy who first predicted that there would be global warming. It was in like 1865. He wrote a paper on global warming. Right? So due to anthropogenic generation of CO2. Anyway, so he did a couple things, but one of them was this Arrhenius equation. I think he's most famous for. Let's see. There. So anyway, if you look at this, so you're going to take this is some rate of something happening, and this is the energy barrier of it happening. So you're going to do like log of k. It's going to go with 1 over t, and it's going to be a negative slope. It's going to be the activation energy for the thing. Right. So over here, it's like this is like commonly used for viscosity. So you measure the viscosity, log of the viscosity goes with 1 over t. The slope of this is the energy of activation for the, like if you had two molecules and the third molecule had to squeeze through, it had to push the other 2 apart. It's the energy of pushing the other 2 apart to pop over to the other side and flow. Right, so that's the activation energy for, so viscosity is always like log viscosity for 1 over t. The slope is the activation energy. So anyway, so that's kind of the Arrhenius equation. Or there's also in the 1960s, this guy Eyring at Cornell came with Eyring rate theory, which is about anything that happens. And it's the same form as the Arrhenius equation. It has to do with like rates of chemical reactions, right? So anyway, so it's the same form, right? And there's also an activation energy in it, right? I mean, I think Arrhenius was vague about what B is, and Eyring was more specifying that this is an activation energy for thermally activated process. But the Eyring rate theory is used for everything beyond what the Arrhenius is used for. Arrhenius is mostly viscosity. Eyring's for chemical reactions, and people have used it to study like migration of animals and things, like at different temperatures, they'll migrate faster. They do a plot of log of the migration rate versus 1 over t, and you can get activation energy for elephants in the savannah. People have done that. I mean, there's a lot of things where people have generally applied Eyring rate theory. So anyway, you're always getting these plots of log of something versus 1 over t, right? So you have Clausius-Clapeyron, log of pressure versus 1 over t. Eyring rate, Arrhenius log of viscosity versus 1 over t, and Eyring rate theory, chemical reaction rate versus 1 over t. And it's log of versus 1 over t. It's like the general rule. And the slope of these things is always something that has units of energy. For the Clausius-Clapeyron, it's the enthalpy. For the Arrhenius, it's activation energy, and for iron rate, it's the activation energy for this process that's going on. Like here, it's showing nitrogen to nitrogen oxide reaction rate, right? So that's two, that's three. Clausius-Clapeyron, Arrhenius, and Irene. And the fourth one is this is a thing that looks almost just like the Clausius-Clapeyron equation. So it's called the Van Hoff equation for chemical reaction equilibria. So when you have a chemical reaction, you have reactants that go to products. This should say reactants here, but anyway, reactants. So you take the ratio of the moles of products to moles of reactants, and that gives you this equilibrium constant for the reaction. This is also equilibrium constant for like metal transitions, like right. So any kind of where you have a reaction that has a transition thing, right? So anyway, so in that case, you write the change in free energy is going to be log of the reaction rate constant, right? Reaction equilibrium constant. RT gives you the enthalpy of the transition, which is the reaction transition, delta H minus T delta S. And then you do the same thing you did with Clausius-Clapeyron. You say ln of K is delta H RT, etc., and you swap out S for T, end up with the same expression as in the Clausius-Clapeyron equation. Then you end up with ln of the reaction constant dt is delta H over RT squared, the same expression, which also gives you a log of the reaction constant versus 1 over T. So it's kind of the same thing as the Clausius-Clapeyron applied to chemical reactions. But the difference is that the model that you use in here is a chemical reaction. The model in the Clausius-Clapeyron isn't. Clausius-Clapeyron is some kind of liquid vapor transition. This is like a chemical reaction going on, right? So you're forming something, you're making chemical bonds. So the one is like a physical, Clausius-Clapeyron is like a physical transition from a vapor to a liquid. And the Van Hoff is a chemical transition where you actually make bonds and things happen, right? So if you're making a model, your model would be quite a bit different for the Van Hoff than it would be for the Clausius-Clapeyron, even though they're exactly the same thing. It's almost like the Van Hoff stole it from Clausius-Clapeyron, but I think they were done in parallel. I think they were separate, but anyway, we're out of time, so I'll quit there. But that's kind of what the homework is, like taking a paper and taking those comparison of those different things. So I wanted to kind of get through that. See if I can get out of this. Any questions, anything?
Is paper online on
Yeah.
that website?
Yeah. So it's on the same place. I just one more thing in there. It's in the homework, right? The homework 2, it's like this paper. Anti-Arrhenius passage of gas. He's got also the Arrhenius equation, this thing. So it's kind of a simple, it's a short paper. It's kind of simple. That's his model. And you can, so this is where he uses Clausius-Clapeyron, but so it's kind of, I don't know, it should be fairly simple compared to last week's, so hopefully, and it's a lot simpler than the one that I used last year for this section. So anyway, so I'll talk about that. I'll go through that next time, on Thursday. So, right. So, real quick there. 1, 2, 3, 4, 5. So one guy's missing. The 6 in here. Somebody is missing. Who it is?